Hey guys, continuing on in Unit 1, we're going to look at exploring types of discontinuities and defining continuity at a point. Okay, so we kind of sort of casually said that if a function is continuous, then to find the limit, you can just use direct substitution, right? But what actually does it mean what does it mean to be continuous? We do kind of have a technical definition. So first off, we'll start with kind of a casual definition here, and then we'll build to our formal definition down here. Okay, so for a function to be continuous, it has to be unbroken. In other words, you have to be able to draw your graph without picking up the pencil. So when is a function not continuous? Well, we can think, well, when do I pick up my pencil? Well, if I have a graph and then all of a sudden there's a hole, well, that would make me pick up my pencil, right? I can also think, well, if I have a graph, maybe it's going like this, and then there's like an asymptote here. That would make me have to pick up my pencil, right? Or kind of looking maybe at this for some inspiration. If I have a jump in my graph, so maybe it goes like this, and then there's like a piece down here. Okay, all of those things would make me pick up my pencil, right? So if I look at this graph, at -8, there's a hole, so it's not continuous there. At -4, this is a jump, right? Because it's on one side and then it jumps down to the other. So I would call that a jump discontinuity. And then at 3, it looks like there's a hole again. When it's a hole, we also call this a removable discontinuity, okay, because it's like if I could just take that one point and plug it, it would make it continuous, right? So it seems like such an easy fix, right? So it's like that point was just removed, okay? We could like unremove it and it would make it continuous. All right, looking at -6, well, a -6 is right here. That's just a point on my function. I don't pick up my pencil there. So that is continuous. And then finally, when x equals 2, it looks like we have a vertical asymptote there, which we also call an infinite discontinuity. So that's not just like one point is out of place, right? That's going up to infinity. And then this side, there's nothing. So that's definitely not continuous there. Okay, so for our formal definition here, we have what we call the 3-part definition of continuity. So I'm going to pause and kind of write our first line here. All right, so a function f of x is continuous at a point C if the following things are met. So first of all, we have to make sure the function actually exists there. That would help, right? So we have to say f of c is defined. Okay, that's the first part. So does the function even exist there? Then if it does exist, is it kind of in line with the trend of the graph? So in other words, I want to know, does the limit exist? So I can think something like this, right? The two sides have to be going towards the same thing. Otherwise, I have a jump, right? Or maybe a vertical asymptote. So I need the limit to exist. So I'm going to say, does the limit as x approaches c from the left of f of x equal the limit as x approaches c from the right of f of x? Okay, and then finally, if the function exists and the limit exists, I want to make sure those are actually the same value. So up here in this graph, right, the limit existed and the function was defined, but it wasn't continuous, right? We needed that point to be, we wanted that point to be here, right? So if that was the case, then it would be continuous. So if we want the function defined, the limit to exist, and we want those two things to be the same value, that makes it continuous. So my final condition here is that the limit as x approaches c overall of f of x should equal what the actual function value is at that point. Okay, we actually kind of said this already when we talked about using direct substitution, right? So these ideas very much go together. Right, so what we're going to do is look at this graph now and try to look at some values and see if it's continuous there. So first off, what is g of a? So if we look at -6, the actual function value, it looks like, is undefined. I don't see an actual point there, so we'll put undefined. The limit as I approach -6 from the left is going to be +5. As I approach from the right, it's also +5. So overall, the limit is 5, right? My left and right are equaling. If you think about putting your fingers in front of your face, right? They're both going to 5, so they're meeting. Now, does the function value equal the limit? Well, no, because the function is undefined. So I would say no, this is not continuous. And then why? Well, I can say because it's undefined, so it fails condition 1. Or I can just say g of -6 is undefined. Okay, let's look at the next one. So if I have -3, that's right here, the function value is that point, so it's up at 2. And as I approach from the left side, it's also equal to 2. But if I go from the right side, it looks like I'm approaching the y value -4. So therefore the limit does not exist there, right? Left does not equal right. So the limit does not exist. So if the limit doesn't exist, then the function can't equal the limit, right? So we would say no here. This is failing condition 2, right? So I can say the limit as x approaches -3 from the left does not equal the limit as x approaches -3 from the right. All right, now 0 has a point right here, and the limit from both sides is equal to that point, right? I don't pick up my pencil at all, so it makes sense that it is continuous there. So if I plug in 0, I get -1. The limit from both sides is -1, so the limit overall is -1, which means these two things are equal. Yes, so yes, this is continuous. Okay, and it meets all 3 of the conditions. So it meets all 3. Okay, I'm going to actually ask you guys to try these last ones. I'll go ahead and pause and show you the solutions. Okay, so here's kind of what we should have for those last values. And on the last one, you can just say the overall limit doesn't exist, or you could say kind of the same thing we set up here, right, where the left and the right do not equal each other. Okay, so let's be a little bit more precise notationally here. And it says use the 3-part definition of continuity to determine if the given functions are continuous at the indicated values of x. If discontinuous, name the type. Okay, so I kind of wrote out, these are the things that I'm looking for. So first off, f of -2. So when x is -2, I have to look at the rules here when I have a piecewise function. So it looks like when x equals -2, I'm following this rule. So it's 3x plus 2, so it's going to be 3 times -2 plus 2, which is -6 plus 2, so that's -4. Okay, then I'm going to look at the limit on each side. So as I approach -2 from the left, that means I'm looking at values that are smaller than -2. So I'm going to be following this rule, okay, values that are less than -2. So I'm going to think of this equation. So what I'm really looking at is the limit as x approaches -2 of -2 root -2 plus x. Oh, whoops. Sorry, x plus 6 is like a weird thing. Okay. Okay, so here I can actually use direct substitution. Just plug in -2 here. And I'm going to get -2 plus 6 is 4. So this will be -2 times the square root of 4, which is just 2. So it's -2 times 2, so I get -4. Okay, and if I try from the right, that means I'm looking at values that are bigger than -2, so I'm going to be following this rule. So I'm going to look at the limit as x approaches -2 of e to the x plus cosine of pi x. And I'm plugging in, I'm going to move this down a little bit. I'm going to plug in -2 there. I shouldn't have a problem doing direct substitution, so this is going to be e to the -2 plus cosine of -2 pi. Okay, e to the -2 is 1 over e squared, which is going to be some crazy decimal. And then cosine of -2 pi, so unit circle, positive angles I go this way, negative angles I go this way, but -2 pi is the same thing. I'm going to end up right here. The x value there for cosine is 1, so I get 1 over e squared plus 1. Okay, now that does not equal -4, so I'm actually going to move this down. I really don't even need this third condition because it's going to fail the second condition here. So I can say the limit as x approaches -2 from the left does not equal the limit as x approaches -2 from the right. Okay, so therefore this is discontinuous. And more specifically, if the limits aren't equal, that tells me I'm in two different places, right? So this place, it's going down towards, or it's around -4, right? And then it equals -4, and then there's a jump, right, to this some positive value up here, and then it continues doing something. So this is a jump discontinuity. Okay, so again, since the limits aren't equal, I can say, I'll say therefore it's a jump discontinuity. Okay, let's go ahead and look at B. All right, so looking at B, I kind of set it up again, looking for these three conditions. So first of all, I want to find what is g of pi, just to make sure it's defined. So if I plug in pi, that means I'm looking at this equation, because this is where it has the equal to pi part. So I'm going to plug in pi to this. Now that looks kind of crazy, but it's not too bad. So tangent of 3 pi over 4. I mean, it's not too great either. So let's see. Tangent of 3 pi fourths. Tangent is the same as sine over cosine. And sine and cosine at 3 pi fourths, if I think of the unit circle, 3 pi fourths is right here. They're both the same, root 2 over 2. So this should be 1. Right, but sine is positive, cosine is negative. So, and I divide this up, positive root 2 over 2 divided by negative root 2 over 2. So this is going to give me negative 1 times e to the pi, so I'll just put negative e to the pi. Okay, then looking at the limits from each side. So as I approach pi from the left, I'm looking at the part where it's smaller than pi, so that's going to be this first function. So I'm looking at the limit as x approaches pi of e to the x cosine x. And I can use direct substitution here. Okay, I don't have any problems. So if I plug in pi, I get e to the pi cosine pi. And cosine of pi on our unit circle is the x value here, which is -1. So I get negative e to the pi. Okay, and as I approach pi from the right, that's going to be this second equation, the e to the x tangent 3x over 4. And I already did this, right? I did direct substitution because it's actually defined there. So here I know that I get negative e to the pi. Okay, cool. So since both sides are the same, that tells me, oh yeah, sometimes I should remind myself, some little notation that I do. These 3 dots here mean therefore. and this arrow means that implies. It's just kind of some math proof notation. So this implies that the limit as x approaches pi from the left equals the limit as x approaches pi from the right. So it meets condition 2. And finally, I know that both of these things equal negative e to the pi. So that's also true. So therefore, I can say g of x is continuous. Okay, and we can also look at this on Desmos. So I'm going to take a moment and type this in and then show you the graphs. Okay, so I went ahead and typed these functions into Desmos, and you can see the part that I put at the end there is called a domain restriction, and so that cuts off the graph where it says. So that's at pi. So down here, if I kind of try to find a point on here, I can go all the way, so it's like 3 point, right? I can get close to pi, but I can never really reach it on the black function because it stops. Okay, it's only for less than pi. There we go. I'm like, it's not really letting me even get close at all. Okay, so then on the red graph, I can actually go to pi. Okay, in fact, if I make an equation that's x equals pi, I can see where it intersects, and notice that it's the red graph that kind of highlights here. When I tap that point, it doesn't really work on the black graph, but if I have the red graph kind of highlighted, it comes up as a point of intersection there. Okay, and it's negative 23 something. We got negative e to the pi, so let's check that that's the same value. That's something else that I can do, so negative e to the pi. Hey, that looks familiar, right? I think that's that same number, negative 23.141. So pretty cool. Again, this is the reason why I think you should have Desmos, right? It's cool to kind of use as a reference for some of the stuff that we're doing. So there's that one. Okay, the rest is practice that I'd like for you guys to do. So we've got a graph looking at these points, and then, oh, that's it. That's all I have for you. So we'll probably do this in either Delta Math or Khan Academy, but go ahead and give these a try, and we'll talk about them next time. Thanks, guys.